Have you ever peered inside the chips that power, well, pretty much everything around us? Your phone, laptop, even your smart thermostat. You use them constantly, right? But have you ever stopped to think about how the different bits inside a single chip actually, talk to each other? Turns out that question, it seems simple, but it opens up this whole fascinating world of engineering trade-offs. Today, we're taking a deep dive into that hidden language, the world of on-chip communication buses. Specifically, we're looking at a protocol called AXI. It's the industry standard, basically. But as we're going to explore, being the standard doesn't always mean it's the best choice. Not for every job, anyway.
That's exactly right. That's our mission today, really. We want to unpack why AXI is so dominant, what makes it powerful. But also, and this is crucial, look at its unseen costs, the trade-offs. Then we'll shine a light on when maybe simpler purpose-built buses, or sometimes even completely custom designed, can actually be way more efficient, more effective. Our goal is to give you a kind of shortcut to understanding these really critical design decisions and maybe spark some aha moments about the incredibly intricate balance behind, well, every piece of electronics you use.
Okay, yeah, let's kick things off with AXI itself, the king, as you said. So the Advanced Extensible Interface, AXI, it's just everywhere in modern system-on-chip designs, SoCs, and also in FPGAs, those reprogrammable chips. ARM introduced it back in, 2003, and then refined it in 2010 with AXI4, AXI4 Lite, AXI4 Stream. And it's royalty-free, open. So it's become the de facto standard for how different IP blocks, those are the pre-designed circuit chunks, how they communicate inside the chip.
Absolutely.
Yeah.
You find it connecting, well, everything. Processors, memory controllers, DMA engines, various peripherals. It's the glue holding it all together. And its core strength, as you touched on, is that standardization.
Right, like a universal plug-and-play system for chip parts.
Exactly. It simplifies integrating IP from all sorts of different vendors. You can build a cohesive system much faster. It boosts productivity, no doubt, by cutting down on design time, implementation effort, verification, all that. Plus, you've got massive toolchain support from the big players, Xilinx, Intel. They have libraries full of AXI-ready components.
Okay, let's unpack this, though, because it's so prevalent, so supported. It sounds like AXI often becomes the default choice, maybe without enough critical thought.
That's precisely the point, and that's where we can fall into what some call the over-engineering trap. It's like using a sledgehammer to crack it sometimes. While AXI is incredibly powerful, all those features can be an unnecessary burden if your communication needs are simple or if you're under really tight constraints.
Give us an example.
Okay, think about something really basic, like a timer or a GPIO port controlling maybe just an LED light. For those low throughput things, AXI is, well, it's huge overkill. All the sophisticated machinery for high-speed bursts to memory just sits there unused. But the logic to support it still takes up precious silicon area. It still consumes power.
Ah, okay. Unnecessary resource allocation.
Exactly, and that directly hits a product's competitiveness, especially if it's cost-sensitive or needs super long battery life or has to get to market really fast. What's fascinating here, and this is sort of the core idea today, is digging into when AXI's overheads, the cost of those unused features actually make it less than ideal. And that's what pushes designers to look at simpler standard buses or sometimes even build something completely custom.
So what does this all mean for the designers, then? It sounds like a really tricky balancing act.
It absolutely is. Choosing the right interconnect is like this multi-dimensional optimization puzzle. You're juggling conflicting goals all the time. You've got performance that's throughput, how much data and latency, how fast it gets there. And there's power consumption, a huge one these days. Silicon area, the physical size or gate count, how much chip real estate does it take, and of course just the sheer complexity of designing it and making sure it works correctly, the verification effort.
Can you give an example of those trade-offs with AXI?
Sure. Let's say you want more performance from AXI. You can increase the data width, make the highway wider, essentially, but that immediately increases complexity and power draw. More wires, more logic. Or you use AXI's advanced features like pipelining, doing multiple things at once, or out-of-order transactions, letting faster tasks jump the queue. Those definitely boost performance, but they also significantly ramp up the complexity, the silicon footprint, and again, the power consumption.
And the flip side.
Well, if your absolute priority is ultra-low power, maybe for a wearable device, or minimal chip area to keep costs down, then you're forced towards simpler architectures. And those inherently limit your peak performance. You can't have it all. So choosing the right interconnect is fundamentally about aligning with the main goals and constraints of your specific project, picking the right tool for that particular job.
Okay, let's dive deeper into AXI itself then. To understand why it's the go-to for demanding stuff, we need to understand its architecture.
Exactly. AXI is, at its core, a robust, fully synchronous protocol, everything marching to the beat of the same clock. It's built for high-performance data exchange on the chip. It's channel-based. Think of it like having separate dedicated lanes for different types of traffic. There are 5 independent unidirectional channels, which allows for full duplex data flowing both ways at once and pipelined operations.
5 channels, what do they do?
You have one for read addresses, telling memory what to read, one for read data, getting the data back, then symmetrically, one for write addresses, telling memory where to write, one for write data, sending the data, and a 5th one for write responses, getting confirmation the write happened. And each of these channels uses a simple, reliable handshake mechanism. A valid signal from the sender saying I have data address, and a ready signal from the receiver saying I'm ready for it. Data only moves when both are active, ensures nothing gets lost.
And you mentioned variants. AXI4, Light, Stream.
Right. ARM created these to tailor AXI for different jobs. AXI4, the full version, is the powerhouse. High performance, memory mapped, great for burst transfers of big data chunks, supports wide data paths, 32 bits up to 512 or even more. That's your superhighway. Then there's AXI4 Lite. It's a stripped-down version, much simpler, still memory mapped, but for low-throughput stuff like control registers. Think simple on-off switches. Crucially, AXI4 Lite lacks BERT capability. It only does single data transfers, and it's usually 32 or 64 bits wide, more like a local access road. And finally, AXI4 Stream. This one's different. It's for high-speed streaming data like video or audio. It's unidirectional, has no addressing, just a continuous flow of data, and the data order is always preserved. Think of a dedicated pipeline.
But even AXI Lite, the simple one, still has some overhead compared to something totally basic.
It does. It inherits some of the fundamental AXI structure, even in its simplified form. So compared to a truly bare-bones custom interface, yeah, there's still a bit more logic involved.
Okay, so let's talk about the performance features of the full AXI4. Here's where it gets really interesting, right? These features are why it's complex, but also why it's so fast.
Precisely. These sophisticated features are the reason AXI performs so well in demanding situations. They are not flaws, they are deliberate design choices for performance. Take pipelining, those independent channels we talked about. They allow different stages of transactions, address, data, response to happen concurrently for different operations. That boosts overall throughput and reduces the effective latency, like an assembly line. Then you have burst transfers. This is huge for efficiency. A single address request can initiate multiple sequential data transfers. Think fetching a whole block of data from memory with just one command instead of asking for each piece individually. Much less overhead.
And the separate read and write channels help too.
Absolutely. They can operate completely independently and simultaneously. You can be reading from one part of memory while writing to another, maximizing the use of the bus bandwidth. And for really high-end systems, AXI supports out-of-order transactions. This means a master, like a CPU, can issue multiple commands without waiting for the first one to finish. If one command gets stalled waiting for slow memory, other commands can still proceed. It helps hide latency and keep things moving. AXI uses unique IDs, thread IDs, to keep track of all these outstanding requests and make sure that data and responses get matched up correctly, even if they complete out of order.
Wow, okay. That sounds powerful, but also complex to manage.
It is. And underpinning all of this are those valid ready handshaking signals on each channel, providing that fundamental flow control to make sure data transfer is reliable. Plus, the whole architecture is designed to be scalable and extensible. You can use AXI in small systems or build massive multi-core chips with complex interconnects, linking many masters and slaves together.
Okay, so if we connect this to the bigger picture, where does AXI really shine? What are its killer applications?
Well, clearly, memory-mapped access is a primary use case. Both AXI Full and AXI 4 Lite are designed for accessing memories and peripherals mapped into the system's address space. The flexible data widths are key here. It's ideal for high-speed data processing. Think video processing pipelines, digital signal processing, DSP, moving large chunks of data between memory and accelerators, high-speed networking interfaces, anywhere you need serious bandwidth. It's also the critical backbone for multi-core processors and DMA engines. In modern SoCs, you have multiple processor cores, graphics units, other accelerators, all needing fast memory access. AXI provides that highway, and DMA, direct memory access, relies heavily on AXI to transfer large data blocks directly between peripherals and memory, offloading the CPU and hiding memory latency.
And the standardization factor comes back in.
Definitely. IP interoperability is huge. Because AXI is the standard, designers can easily integrate pre-built, pre-verified IP blocks from third parties. This fosters modular design, speeds up development immensely. And finally, that toolchain support we mentioned. The major FPGA and ASIC design tools like Vivado and Quartus have deep integration with AXI. They provide tools to automatically generate interconnect logic, verify AXI interfaces, and offer libraries full of ready-to-use AXI-compliant IP cores. Honestly, for complex systems, this robust ecosystem often outweighs any theoretical marginal gains you might get from a simpler solution, just because it dramatically cuts down design time and, crucially, verification effort. The total cost of ownership often ends up being lower with AXI, despite its complexity.
Okay, so we've established AXI as this powerful, well-supported standard essential for complex, high-performance systems. But now let's pivot. What happens when that power comes with, well, unexpected baggage? You mentioned unseen costs earlier. Let's unpack those.
Right. Despite all its strengths, AXI isn't free. Its inherent complexity directly translates into overheads. First, there's area and gate count. More features, more channels mean more logic, which means it takes up more physical space on the silicon chip. We have some data points suggesting AXI monitoring logic alone can take up a noticeable area.
Yeah.
And compared to a simpler bus like AHB, AXI's multi-channel structure inherently uses more gates.
And that usually means more power too, right?
It does. More gate switching means higher power consumption. Studies have shown AXI can consume significantly more power, maybe around 50% more than AHB, for similar tasks, just because of its more complex architecture. Now, AXI does support power management features. You can gate clocks or power down sections. But the core interconnect logic itself might limit how aggressively you can optimize power at the system level. And for those ultra-low power IoT devices we talked about, running on tiny batteries, maybe needing microwatt level power, AXI's baseline power draw can just be too high. It could be prohibitive. Also remember, AXI is fully synchronous. The clock network distributing that single clock signal across the chip can itself be a major power hog, maybe 20–30% of the total chip power. Simpler, maybe even asynchronous, alternatives can offer a much clearer path to ultra-low power.
Okay, so area and power are costs. What about performance itself? You mentioned latency issues.
Yes, latency challenges and even deadlock potential. While AXI is designed for high throughput, which can mask latency, getting true low latency can be tricky. For instance, if you have parts of the system running on different asynchronous clocks bridged together, the synchronization process can introduce significant delays, sometimes dozens of clock cycles. Even in fully synchronous systems, certain configurations or traffic patterns can cause unexpected stalls or even system hangs. And remember those powerful out-of-order transactions. That's the double-edged sword of parallelism. Well, allowing multiple commands to be outstanding at once boosts throughput, but it dramatically increases the complexity of managing the state of the system. There's a real risk of creating deadlocks, situations where components are stuck waiting for each other in a circular dependency if the design isn't meticulously crafted and verified. You can get situations like physical priority inversion, where a high priority request gets stuck behind a lower priority one that's holding up a resource simply because of the queuing structure. This raises an important question. Is that potential for peak throughput always worth the headache of managing that complexity and the risk of these hard-to-debug deadlock scenarios? For many applications, maybe not.
And that complexity must bleed into the design process itself.
Immensely. That's the final big cost. Design and verification complexity. An AXI interface can have, over 100 signals. Implementing it correctly, following all the rules about burst addressing, crossing 4 kilobyte boundaries, it's genuinely complex work. And verifying it, that's often the biggest challenge. You need sophisticated verification environments, usually using methodologies like UVM, and you need to run massive numbers of constrained random tests to try and hit all the corner cases. It's not uncommon for teams to spend, say, 60% of their functional verification time just building the test benches and debugging the AXI interactions. Even formal verification methods, which use mathematical proofs, can struggle with the sheer size of the state-space AXI creates. So this translates directly into significant hidden engineering costs. Thousands of engineer hours, expensive licenses for specialized EDA tools, and potentially longer time to market. There really is a direct trade-off. AXI's high-performance features inherently lead to high area, high power, and high complexity. Simpler buses offer savings in those areas, but at the cost of peak performance.
Wow, okay. So AXI is powerful but costly. We've seen its strengths and now its significant drawbacks. But you mentioned simpler alternatives. When you need something leaner, more efficient, Where do designers turn? It sounds like for many tasks, less really is more.
Absolutely. And this is where sticking to the right tool for the job principle really pays off. Let's look at some standard, simpler buses within the same ARM AMBA family. First up, the Advanced Peripheral Bus, or EPB. This is truly the low bandwidth champion.
Low cost, low price.
Exactly. Its entire design philosophy prioritizes minimal cost, minimal power, and reduced interface complexity. It's not pipelined like AXI or AHB. Each transfer is very simple, typically taking just 2 clock cycles. A setup cycle to put out the address and control signals, and an access cycle for the actual data transfer. It has far fewer signals than AXI, maybe just a handful, and the timing requirements are much more relaxed, making it easier to implement. Key signals include things like penable, to signal a valid cycle, and PREDI, the slave's ready signal, PWrite, direction, and maybe PSLVer, error signal. There's also PPROT for basic access control, like distinguishing normal versus privileged access.
And where would you use APB?
It's ideal for connecting those low-bandwidth peripherals we mentioned earlier, things like UARTs for serial ports, SPI interfaces for simple sensors, GPIO pins, timers, keypad controllers, basically anything that only needs occasional register access for controller status updates. AXI, even AXI Lite, is considered huge overkill here. APB is purpose-built for this job, avoiding the cost of features you just don't need.
Okay, so APB for the really simple stuff. What about the middle ground?
That's where the Advanced High Performance Bus, or AHB, comes in. It sits right between APB and AXI in the AMBA hierarchy. AHB offers a balance between performance and design simplicity. It's a single-channel, shared bus architecture, meaning multiple components, or masters, share the same set of wires, and an arbiter decides who gets to use the bus at any given time.
So simpler than AXI's multiple channels, but more capable than APB.
Exactly. It supports features like burst transfers, pipelined operations, allowing the address phase of the next transfer to overlap with the data phase of the current one, and multiple bus masters. What's fascinating here is that for certain types of traffic, particularly smaller bursts like 16 or 32 bytes, AHB can actually achieve lower latency than AXI.
Really?
Because its arbitration scheme is simpler, getting access to the bus takes less time compared to navigating AXI's more complex channel structure and potential dependencies. AHB generally achieves pretty high bus utilization, maybe 70–80%, across different burst sizes. It's really a sweet spot for many embedded systems, particularly those based around ARM Cortex-M microcontrollers, which often don't need the absolute peak performance of AXI, but do need something more capable than APB. In fact, complex chips like the Yilling's Zinc devices cleverly use all 3 AXI for the high-speed processor memory connections, AHB for intermediate peripherals, and APB for the low-speed stuff, all connected via bridges. It's a great example of optimizing resource use by matching the bus to the need.
That makes a lot of sense, tiering the communication based on requirements. But what happens when even these standard alternatives, APB or AHB, aren't quite right? What if you need something truly extreme, hyper-fast latency, or practically zero power? Do you just hit a wall?
Not necessarily. That's precisely when designers start seriously considering custom bus architectures, going beyond the limitations of standard protocols. The main driver is when the inherent characteristics or overheads of any standard protocol, even the simpler ones, become the primary bottleneck, preventing you from meeting your design goals.
What kind of scenarios push you towards custom?
Several specific situations really compel custom interconnects. Ultra-low latency requirements. We're talking situations where delays measured in nanoseconds or microseconds are simply unacceptable. High-frequency trading is a classic example. Real-time industrial control loops. Certain scientific instruments. Standard bus protocols just have too much inherent overhead. Extreme power constraints. Think microwatt-level operation. Batteryless sensors. Implantable medical devices. Extreme edge IoT. Here, every single nanowatt counts, and the baseline power of even APB might be too high. You need something stripped down to the absolute bare minimum. Highly specialized data paths. If your application has a very unique, predictable data flow pattern, maybe complex signal processing, custom video algorithms, specialized AI accelerators, a standard bus might be inefficient. A custom path tailored precisely to that flow can be much better, and integration of legacy or proprietary IP. And sometimes you have existing IP blocks, maybe older designs or third-party components with unique interfaces. Rewriting them just to add an AXI wrapper can be hugely expensive and time-consuming. Building a simple custom bridge or a small custom bus to integrate them can be far more practical. This really highlights the limits of standardization. Standardization is great for interoperability, but sometimes the overheads it imposes just don't align with extreme requirements.
Okay, so if you go custom, what does that actually look like? What are the options?
They range from the incredibly simple to the quite complex, depending on the need. At the most basic level, you have simple handshake protocols. The most common is probably valid ready, just two signals. Sender asserts valid when it has data, receiver asserts ready when it can accept it. The transfer happens when both are high. It's minimalist point-to-point communication, very common inside synchronous designs. You can also have simple request acknowledge schemes.
And you mentioned asynchronous possibilities earlier.
Yes, asynchronous or clockless circuits are a fascinating custom approach, especially for low power or high speed in specific scenarios. They don't rely on a global clock signal. Instead, they use handshaking protocols between components not just for flow control, but for timing itself. Completion of one stage triggers the next. This makes them robust to clock skew issues, potentially faster because speeds are limited only by gate delays, not clock cycles, and often much lower power because logic is only active when doing work potentially zero standby power. It's truly minimalist communication.
Interesting. What else is in the custom toolkit?
FIFO-based interfaces are extremely common. FIFO's first-in, first-out buffers are essential building blocks. They act as elastic buffers between components, smoothing out data rate mismatches, handling synchronization between different clock domains, or just providing temporary storage. They can be simple shift registers or based on small memories. You can have synchronous FIFOs using clocks or asynchronous FIFOs using handshaking. They provide crucial decoupling and buffering, often without needing a full bus protocol.
And what about moving lots of data, like DMA?
Right, so you can have specialized data paths. DMA itself, direct memory access, while often interacting with standard buses like AXI, is a specialized hardware block designed for efficient, large-scale data transfers independent of the CPU. Using DMA instead of having the CPU manage transfers over AXI is a common optimization strategy. You can also design custom streaming interfaces specifically for applications like DSP or video, where you have continuous high-volume data flow. These interfaces prioritize raw throughput and minimize protocol overhead, often looking like simple point-to-point connections, perhaps with FIFO buffering. It's all about optimized data movement for a specific task.
And for the really big, complex chips?
For highly complex SOCILs with dozens or even hundreds of IP blocks, designers might opt for application-specific networks on chip, or NOCs. This approach borrows principles from computer networking, using routers and packet-based communication within the chip itself. Instead of long shared buses, data travels in packets across a network of small routers connected by short links. The benefits can include reduced wire routing congestion, which is a huge problem on large chips, easier timing closure, potentially higher operating frequencies, and more flexibility in placing IP blocks. And again, asynchronous no-saves are an active area of research and development, showing promise for significant reductions in area, latency, and especially power compared to synchronous no-saves. This really enables scalability beyond buses for the most complex designs.
That's a whole spectrum of custom options. Can you share some real-world examples where these custom approaches really made a difference?
Absolutely. There are some compelling case studies. For ultra-low latency, look at the world of high-frequency trading. Companies develop specialized FPGA-based network interface cards with highly customized Ethernet MAC and PHY logic. These custom designs can achieve round-trip latencies from network wire through the FPGA processing and back out measured in mere tens of nanoseconds, orders of magnitude faster than standard solutions. Another example is UA-Link, an open standard being developed for connecting AI accelerators. It aims for massive bandwidth, 200 gigabits per second per lane, and targets microsecond-level latency across large clusters of potentially over 1,000 accelerators. That requires a highly optimized custom physical layer and protocol. This is pure latency-driven design.
Incredible speeds. What about the other extreme, power efficiency?
For extreme power efficiency in IoT, we see amazing integration. There are Wi-Fi chips designed for IoT that consume as little as, say, 28 microwatts in certain modes. That's thousands of times less than standard Wi-Fi. They achieve this using custom techniques like backscattering communication and having tiny, ultra-low power wake-up receivers that sip maybe 3 microwatts while waiting for a signal. Standard protocols just wouldn't allow this. Or consider specialized hardware for things like real-time video tracking on drones or robots. Custom SoC FPGA platforms using optimized data paths and accelerators have been shown to perform complex tracking tasks using around 5 watts. A traditional CPU-GPU system doing the same job might burn over 200 watts. That's power-constrained innovation driven by custom hardware.
And integrating tricky IP or specialized path?
Yes. For highly specialized data paths and IP integration, custom solutions are often the pragmatic choice. In high-performance DSP, you might see designers use direct point-to-point connections between processing blocks, maybe even integrating bare DSP guides directly onto a circuit board to minimize distance and optimize signal integrity, bypassing standard buses altogether. We also see custom bus work being done simply to retrofit new components into existing systems, like industrial control or power infrastructure, where matching legacy interfaces is critical. And for complex SoCs integrating IP from many sources with different native interfaces, maybe some use OCP, some ABB, some older proprietary buses, using a configurable network on chip, like Artur's Flex NoC, is often preferred over forcing everything onto AXI. NoC acts as a universal translator, efficiently bridging all these different protocols, data widths, and clock speeds. It's a prime example of application-specific optimization winning out over rigid standardization. So to kind of circle back to the big picture, AXI is absolutely an indispensable standard, especially for complex high-performance systems. Its features are powerful, and that ecosystem is just invaluable.
Right. It's the king for a reason. But as we've really dug into today, it's definitely not a universal solution, is it? That over-engineering trap is real. And the overheads area, power, complexity, they can be serious deal breakers for simple designs or those pushing the absolute extremes of performance or efficiency. Choosing the right on-chip interconnect, it's always this critical, multi-dimensional trade-off, no single answer fits all.
Exactly. So if we were to boil it down to core recommendations. Choose AXI when you genuinely need that high throughput, when you have multiple masters and slaves interacting complexly, and crucially, when leveraging that third-party IP ecosystem and tool support is a major advantage for your project timeline and resources. Consider simpler standard buses like APB or AHB. Use APB for those truly low-bandwidth peripherals registers, simple controls where its minimalist design saves significant cost, power, and complexity. Look at AHB when you need a solid balance of moderate performance and simplicity, maybe for embedded systems where AXI feels like overkill but APB isn't enough. It's a well-proven sweet spot. And opt for custom bus architectures where there's simple handshakes, FIFOs, specialized paths, or even no fees when you're facing those extreme requirements. Ultra-low latency, ultra-low power, highly specialized data flows are really challenging IP integration problems where standard solutions just create bottlenecks.
It's fascinating stuff. When you think about it, what stands out to you, our listener, about how these really fundamental, deep down engineering choices shape the technology we interact with every single day? This kind of precise, deliberate engineering, choosing the right level of complexity. It's not just about silicon, is it? It feels like a powerful lesson in making that right tool for the job choice everywhere. And how sometimes actively avoiding the overkill solution, the default standard, can lead to incredible efficiency and really drive innovation. Makes you wonder, where else in your world is the default? Maybe not the optimal solution?